with midas NFX CFD. So I'm Cyprian, the NFX International Technical Manager, and I will be the presenter today of this webinar. So here's the summary. We'll have 4 parts in this webinar. Firstly, I'll introduce briefly midas NFX CFD for those who don't know the software. Then I'll talk about some main analysis issues that a lot of people are analyzing using fluid analysis, and then I'll show you some basic functions of the work environment and the pre-post of midas NFX CFD. Then we'll talk about the we'll do a technical, practical example of external flow around the model to show you the workflow and how it's easy to simulate such model. And finally, I'll talk about briefly the new function that have been integrated for NFX 2014 in CFD. So first of all, the external flow. So today we'll talk about that, and I hope at the end of today's webinar you'll be able to simulate that in NFX CFD. So NFX CFD is quite a generalist fluid dynamic analysis software, and you have some features to analyze the models in all these industries. So we have clients mainly for heating devices, electric, electronic equipment, plants, fluid machinery, automotive industry, marine and offshore construction, and also aeronautics. And what is actually midas NFX CFD? So first of all, of course, you have a CFD solver, which is integrated into NFX GUI platform, which consists of a preprocessor and a post-processor to get the result and to make the model. And all that is integrated in one software, so you don't have to go from one software to another. And the good thing is that it's also integrated in the same environment than the structural NFX. So it's the same. And if you already have NFX structural, you can very simply add the module for CFD and then perform CFD analysis in exactly the same way. So you will be starting and doing CFD very quickly. Now NFX CFD has a lot of capacity. We have 5 modules. Of course, general fluid flow are the main topic, but we can analyze fluid and heat transfer, coupled analysis, and you can consider as well solid parts and fluid parts. I will do a webinar about that, I think, in 3 weeks, so don't miss it if you're interested by the topic. Then you can analyze the concentration of species inside the fluid. We have multi-phase flow and mesh deformation. Moreover, 14 turbulent models, so if you're in the turbulence, you can do that. We have a lot of benchmarks who prove the accuracy and the stability of the software, and now it's newly added parallel computing using the GPU, so I'll talk about that at the end to show you what it is. A thing you should know about NFX CFD and NFX as well is that the software is in perpetual evolution, so we are adding some new features every year to make it better, and all developers are really working hard to get the best-in-class CFD analysis tool. Now let's talk about the main analysis issues in the fluid dynamic area. So fluid dynamic is used for a lot of purposes. One of these is to analyze the performance of your product. So when you have a liquid flowing inside, it can be a gas as well, and you want to know what is the flow rate at a section, for example, or you want to know what is the velocity in some small areas. So you can use CFD to do that. So you have a few examples here, and I'll talk about the workflow a bit later, but it's easy to model that in NFX and get the report with the details about the analysis. Now, you can also analyze the product durability, which is very important, because when you have rotating equipment, for example, you have a lot of pressure of the fluid on your structural model, and maybe you'd like to know how long I can use this system before it breaks because of the pressure, or maybe you want to check the design and know if the design is correct, there's not too high fluid pressure on some part of it. For example, if you have a valve system here and you want to know the pressure on a specific part when you open the valve, so it's a very basic problem, then you can do that in CFD. Or maybe sloshing also can be analyzed. Then another type of problem is the heating or the cooling of some devices. So mainly we are analyzing the electronic device and electric device. So here you have some example of LED equipment, natural convection, and PC board cooling. So you have a fan and you want to know what is the cooling rate of your PCB. And then you can export the temperature on your structural model to get the deformation due to the temperature, for example. So these can be done as well. And when you want to analyze the flow outside the product, so this is the main topic of today's webinar, I'll show you in the next example how you can do that easily. So it can be around a building or around a car or maybe around a wind turbine. And good thing is in NFX you can export the pressure and apply it on the structural model to get the deformation of the structural model. It can be a flow inside a building or maybe inside a mechanical part as well, of course. So if you have some fans, you want to know what is the rate of the cooling. And some people are also investigating the free surface problems, so the wave analysis due to the bolts. So NFX can do that as well, and we have a tutorial which is available on the website, tutorial section if you're interested. Okay, now briefly I'll talk about the work environment so you understand better about that before we go into the real simulation and show you how to do that. So first of all, the thing you should know is that NFX has two modes, one for designers and one for analysts. So if you're a designer, you want to do quick analysis, just put your model inside and quickly assign boundary and get the result, you can use the designer mode. Otherwise, if you want to analyze a more complex model and have some very specific meshing tool and check the mesh quality or such kind of thing, you'll have to go in the analysis mode in order to get a better modeling capabilities. And in the two modes you can use all the functionalities of the NFX CFD solver. NFX supports 12 types of CAD files, so if you have SolidWorks, Inventor, Solid Edge or Creo, or maybe another type like HyperWorks, you can import all these models directly. And this is the basic workflow. So it's easy to import any CAD model. So you just take the model you have, and then you can create a fluid volume directly into NFX. And you use this fluid volume to apply the boundary condition and the loads. You can use the auto meshing to get the meshing and get the results and output that into a report. So here you have the MS Word format report type, but we have also another type which is the 3D PDF. Right. I'll show you a picture right after. So as I was saying, it's easy to create a fluid volume using the fluid extraction tool. So you can create the fluid inside your part. And NFX has some tools also to simplify the CAD model. So in the case you'll have a lot of small holes or small sorry, I passed some pages, small fillets. It's easy to remove all that before going into the simulation. It's particularly useful when you're doing CFD because CFD models need to be simplified to get good mesh and accurate results. Now about the process and the report generation. So as I was saying, there's a lot of features to get the result you need: the vector output, the contour, the isosurface. You can calculate automatically the flux at any section of the model. You can get the flow lines, and finally you can export your result into a report in MS Word format. So it's very convenient because you can modify the report manually afterwards. You can add some annotation and everything. And 3D PDF. So this is a new feature of NFX 2014. You can export your model in 3D PDF and rotate the model zoom inside the PDF. So you can send that to anyone, even if they don't have the software. They can check your results inside the PDF. So it's very interesting. NFX CFD has also a parallel meshing, so the meshing is quite fast, and it uses all the cores of your computer. So if you have 4 cores or 8 cores, it will be really fast and mesh a lot of parts at the same time. And you have tools to check the mesh, because it's very useful in CFD, especially to be sure that you have a good aspect ratio to get the correct result. And NFX has some kind of fluid structure interaction as well. So what you can do is do the CFD analysis, and when you get the final fluid velocity and pressure result, you can export the pressure result on the structural model. So you can create separately your structural model and export it as a load, and then check the structural results. So I'll show you that right after during the demonstration, how you can do that. And also NFX CFD has some verification examples and some benchmarks. So you can be sure that the result will be accurate. We are always putting a lot of efforts for the quality of the results. Okay, now we are already to the simulation part. So this is the part when I show you how to simulate the external flow around this model. So this is a solar panel, at least a simplified version of the solar panel. And what I'll do is apply a 10 meter per second wind velocity, and I would like to see what happened. So the purpose will be to investigate the flow around the object and to show you how to assign the atmospheric pressure boundary condition and also the steady state condition in CFD. Okay, so let's go into midas NFX. Here it is. So if you can't see the software, please send me a message. I hope it's fast enough, because sometimes the speed of the internet is a bit slow and it's delaying, but anyway. Okay, let's go on. So the first thing I'll do is open a new analysis case. So I'm in the analyst mode. I will use 3D model and meta unit, and I will import a CAD model. So what I will perform today is actually a tutorial which is available on midas NFX website. So if you want to take a look and make it again by yourself, you can go on this tutorial section of midas NFX website to download it and to try. Okay, so now I imported my solar panel. So you see it's the structural model. I have one part, and now the first thing to do is to create the fluid volume which will be around this part. So first thing is, let's define the grid, because you see it's too small. So I will choose 1 meter for the size. Okay, it's better. And I will use the box here to create the fluid volume. So the box size will be 4 meter, 6 meter, and in height 3.5. And I can directly select here on the screen and click to create my box. So this first step to create the box around. So you see that the box is a bit longer in the y direction because I want to analyze the fluid which is below the solar panel. So I need to create a sufficient fluid area. And now the thing is that I have only a box for the moment, so I need to simulate the solar panel which is inside. So I will use the simple Boolean operation to cut these, to cut the solar panel model. So to select the solar panel, you have several ways to do that, but I prefer just to go in the walkthrough here and to select directly the solar panel part, so it will be selected inside. And if I see the preview, you see that it will give something like that. So I click on OK, and now I see that it's working. So my solar panel is inside, and I created the volume, which is around. So next step is I want to see what is going inside, because it's better to assign the boundary condition. So I just click on this part, right click, and change the display mode to line only. Okay, so now it's transparent, so I can view better. So I'll hide the grid and the local coordinate system, and I will hide the structural solar panel inside, because here it's fluid analysis, so this is the only thing I need. So the next thing to do is to create the material for CFD. So I go into the CFD tab here. So here you have all the options to perform the CFD analysis. So I click on material, and by default I have already one material, but this is a structural material, so I don't need it. I will delete it. And let's create a fluid material for CFD. So I have a small library for materials, so I'll choose air at 25 degrees Celsius. And I will use a simple incompressible model, of course, in this simple example, but you have to know NFX can also simulate compressible flow. Okay, now I have to create a property. So for those who don't understand what is the property is here to assign your material data to the mesh. So it's a kind of link to the mesh set. So very simply I can create one property here, and next thing is to assign the boundary condition. So I could mesh the model and then assign the boundary condition on the mesh, but the best is to assign it directly on the geometry. If you do that, it will be more convenient later on, because you can delete the mesh and remesh, and your boundary condition will stay on the model. They will not disappear, so you don't need to recreate everything again. Okay, so first of all, the most important is the inlet. So what I told earlier is that it will be a velocity of 10 meters per second, so I just enter 10 meters per second. I call it inlet, and I click on OK. So you see I created the inlet. Same for the outlet. So outlet will be 0 pressure, so it's a pressure outlet, and in this case I'll consider that the outlet is at the atmospheric pressure, so 0 PA will be the right value. So you'll have to know that in NFX CFD and I think in all CFD software the pressure is defined relatively, so this is why the value is 0, but the actual value is the atmospheric pressure, which is a constant and which is defined in the options. Okay, so click on 0, assign it. Now I have the inlet and outlet, and I need to assign some wall condition. So when you have a solid parts inside a flow, you need to define a wall around this solid part. So I click on wall, and I have to select my solar panel here. at least the surfaces of the solar panel, and choose the type of wall I want to use. So the most basic is the no-slip wall. So what it does basically is that the velocity at the boundary condition for a no-slip wall is 0. So this is the basic condition. So, okay, so I assign that. And now I have 3 faces which are free. No, so I have to assign boundary condition to these surfaces. And one of the tricks in this analysis is that what I will choose is I will do an hypothesis and define that the velocity which is perpendicular to these surfaces will be 0. So this is the boundary condition I will assign. So I go into velocity assignment. Let's select the top face, and here check VZ and just put it at 0. So I'll give it a name, VZ top. Click on apply. And now I have to do the same for the 2 sides, but this time it will be Vx, which will be set to 0. So let's call it VZ sides. Okay. Now my model is almost ready. So you see it's not very difficult. Only basically an inlet, an outlet, a wall condition, and some velocity condition on the other boundary. Now I'll go for the mesh generation because CFD is always using the mesh. So, and the first thing is that you know that I want to know a bit more accurately the flow which is going around this part. So for that, I'll use the size control to make smaller mesh around these parts. So I'll select the edges here, and I will import a value of 0.05 meter, and click on the preview button to be sure that it's small enough and not too small. If it's too small, of course, you'll have better result, but it will take more time because you'll have more mesh. So I click on OK, and now I can use the 3D auto mesher to generate my meshing. So go in the advanced option, and if you need a bit more option for your meshing, you can go in the advanced option. So here I have only one part, so I don't need to merge the nodes. So I uncheck this option. These 2 options are if you want to manage a bit more accurately the size of the element inside the volume. So you can set a smaller value here, for example. Or you can set a minimum volume layer. So if you have a small, let's say like a plate, for example, so the thickness is small, so you'll have to set more volume layers, and some options for geometry proximity when you have small imperfection. And in CFD it's better to uncheck the high order element option because it will give you better results. So it's a specificity of the algorithm, so remember to uncheck this option. Okay, so 02, I check the preview and click on OK. And now I have my mesh. So now that I get the mesh, there are several things to do. The first thing to do is to be sure that your mesh is good enough, so you don't have some wrong mesh, wrong shape mesh inside. So to do that, the best is to check the mesh quality here. So you have some option in the mesh tab, check the mesh quality. And the most basic type of check is the aspect ratio, which will calculate the ratio for the highest mesh edge side against the smallest. So here I click on apply, and you can see here in the text window that it's written per element count 0, so minimum and maximum. So you have a very good aspect ratio, so the mesh is super, I don't need to change anything. If you had some wrong mesh inside, it will be shown in red, so you know in which place you need to remesh the model to get accurate results. Close that, and Actually, what I would like also to check is to be sure that the mesh distribution is good. So to do that, I use the clipping plane function, and I will display the mesh on the edges like that. And you can drag and drop the plane to see the mesh around. So you see you have a nice gradation around this model, and here you have much bigger mesh. So if you think this mesh is too coarse in this area, you can use the advanced option in the meshing to get smaller mesh here around. But for this example, it's enough. So let's close that. And now I'm ready to create the analysis case. So you have two types of analysis case in CFD. You have the steady state analysis case, and you have the transient type analysis case. So these two types are very different type of analysis, so don't take one for another. So what does it mean? Actually, steady state means that you don't really consider the time in your analysis. You're only interested in the final results, so the final distribution of liquid around your model. So let's say there's a very long time going on, and you want to know after this very long time what I will have, what will be the velocity field or the pressure field around my model. So you can use the steady state. On the contrary, if you're interested by the time factor, so you really want to know every second how the fluid is changing inside the model. So if you have inlet which is depending on time, for example the sinusoidal inlet, so in this case you'll have to use a transient type of analysis. So here I'll do steady state, so I click on steady state, I'll give it a name, and so in this window you'll have all the mesh sets. So you see here the mesh set that I defined earlier. This is the CFD boundary condition I defined, and here the active part set. So if I click on this button, I can assign all that. So you have to be sure that the mesh sets are assigned in this area. It happens that you delete the mesh set and the mesh sets go back in this section, so you have to drag and drop it again with the mouse in this section. Okay, now click on the analysis control, and here it's a very important part because CFD is very dependent on the parameters you are inputting in the analysis control. Why? Because all these parameters are controlling the algorithm which will solve your problem. So you have the basic modules here. So if you want to analyze fluid heat transfer, you have to activate that. But here I only analyze fluid flow, so this one is okay. In advanced module, you have the other modules that I taught previously, so specific advection, the mass deformation, and the free surface. Now, the time increment is important, but in steady state it's not so important, because actually in steady state analysis the software is calculating automatically the time increment. So if you input 1 second and the software thinks it's too high, it will automatically decrease this time increment. But this is not the same in a transient analysis, so be careful. If you are in steady state, it's not really important, so you can input 1 second, for example. Number of steps, so let's say 1,000, so it's better to be high. And the total analysis time will be the time increment multiplied by the number of steps, so this will give you the total time for the simulation. Also, this type of steady state doesn't really consider the time by increment, but it has to give you after a certain time I reach the steady state, so this is why you have to some kind of definition of the time. Okay, so this is the intermediate output request. So if you don't want to output all the result, but only the result every 5 steps, for example, so you can import 5 here. Now, module data. So in the module data, you can define turbulence model. So NFX has a lot of turbulence models. The one I will use is the two equation K epsilon. And now I go into field definition window. So basically here, if you have some velocity or pressure depending on a function, so depending on time or depending on x, y, or something like that, you have to create a CFD function and assign it here. Otherwise, you don't need to move that. You don't need to touch that either. But if you're using turbulence, then you'll have to define the eddy kinetic energy and the eddy length scale. So it's important. So I don't give you the formula to calculate that, but if you download the tutorial from the website, you'll have the formula inside, which will tell you how to define these values. So here in this example, it's 0.00135 and 0.0034. I'll click on OK. And finally, the inner iteration, it's kind of, how to say, if you see that it's difficult to converge, so your solution is kind of difficult to get the result because it happened in CFD that your model is quite complex and maybe the pressure is difficult or the velocity is difficult to converge, so you can increase the inner iteration, so put 2 or 3, and inside the solver it will give a supplementary iteration, so it will be much faster to converge. So now it's almost okay. I have a last thing to do. The thing is that when I'm solving this model, I only see the norm of the error, so which gives me the convergence status. So I'll talk about that a bit later. But I would like to know what is the velocity, what is the pressure at some point of my model during the computation to be sure I get the good results. So to do that, you have a result monitoring option, so I can click on it and define a point on my model, so it can be any node of the model. So here the inlet, and as I fixed the velocity at the inlet, so I will check the pressure on the inlet, and I will put another point at the outlet where I will check the total velocity because I fixed the pressure. Okay, now it's done, and I can just launch my analysis. So first I'll save this model. Okay. I save it here, and let's solve. So as soon as you launch the solving phase, you see you have a graph which appears. So this is called the CFD norm graph, and what this graph is actually meaning is that it's giving you the status of your analysis, if your model is converging or not. So basically you have two curves right now, because you have velocity in red and pressure in green, and you have the status of the value of the norm here. So basically this is giving you the error in your analysis. So you see at the beginning you have a very big error, because this is the first step, this is first iteration, and as you run the analysis several increments, the error decrease, and it's reaching a certain state. So when you can consider you have the convergence in your model when this curve goes below this value, 0.001. So when it goes below this value, you see here in the text window to the right, converge, so it means you'll have good results from this step. So when this is why you have to wait a long time before getting accurate result. But you can also stop the analysis at any time and check the result, and if you think it's not correct, modify some parameter and start again. So there's two other graphs here that are the one I give for the monitoring. So you can check that. So first of all, the total velocity at the outlet. So you see here you have, so when the software is running, it gives you what is the value of the velocity at the node I checked at every increment. So you can check if it's reaching a steady status, then it means that you got what you want, because we are in a steady state. And in steady state, basically, the velocity should be stable after a certain increment. So you see here now it's still going down, so it means that you still have to wait until it reaches stable status. Same for the pressure. So the pressure is already stable around 0, so there's no problem. And if you're really pressed to see the result, but you don't want to stop the solver, there's one way. You can directly go back to your model file, right-click in your analysis case, click on Open the result file, and here select CFD result file, check the result file of the analysis you are performing right now, click on Open, and ta-da! You will be able to see the result when the solver is still running. So this feature, I find it awesome. You don't need to stop the solver, you can check what's happening. So this is the latest calculated stat, so you don't see anything, but I'll use, for example, the clipping plane to see what's going around inside my model. So I'll have something like that. So I prefer to use the fringe view. I don't know if you prefer also, but I don't know why, it's better to see. And you see that you have the result during the analysis, so it's very good. You don't need to wait until the end. You can check directly, and you don't need to stop. But by the way, if you stop the solver and you check the result, it's possible to restart from the step you stopped. So you have to check the restart function, and then you will be able to do that. Okay, I'll wait a few more steps. Or maybe I just, okay, I will stop that, and I will open some file on which I already made a longer analysis, so I don't need to wait too much longer. Okay, so I think, yeah, I didn't calculate everything either, but anyway, it's not really important for this case. So I have two types of result, the pressure and velocity. If I want more result, I can right-click and insert analysis result, and you have more types. So here I only have these two, but if you consider temperature or all the types of results, you may want to add some results. So as I was showing you, you have this clipping plane to check the result like that, or maybe like that. You can also rotate directly like that, so if you want to take your own angle or something like that, it's easy. You have the ISO surface, so let's say I want to know, oh, I'm in centimeter right now, I don't know why. Put it in meter again. Okay, so for example here I will be able to check the velocity which is higher than 11 meter per second, and you can use the auto range, which is a good feature that has been added, and give you better visualization of the colors. So you see this is velocity higher than 11, so I can check also the velocity lower than a certain velocity, so lower than 6 meters per second. You see on all this area around will be lower than 6 meters per second. And if you want, you can add some surface. So a different ISO surface can be added. Okay, so this is the first type of thing you can see. Second type is you want to check what is the flow path around this model. So I check this analysis case, and then you can check any node in your analysis and view what is the flow path around. You can also animate all that if you want to view the flow like that around. So just okay. Okay, let's close that. Now you have all the tools for CFD, the flow quantity and the fluid force on the wall if you want to examine that. But the thing I would like to show you is how you can export the CFD results and apply them on a structural model, because it's something that you may want to do. So for that, the first thing is to be sure that your mesh are activated. Yes, okay. Now go into the results tab and you have a function called extract. So with this function you can extract the result as tables, and I will extract the pressure. Before I do that, I'll show you what it looks like in, let's say, the visual view. So you see this is the solar panel and this is the pressure around. So basically what I want to do is export this pressure distribution and to apply my structural model. Okay, so it's just to show you what I want to do. Okay, extract pressure. I'll select the analysis case I want to export the pressure. Extract the node, and now I have to select the part of my model. So to select more conveniently, I will hide the mesh, and I will also hide the solid part, and now I can go in the selection tool, select face, and select the faces of this. So if you do that, all the nodes which are on these faces will be automatically selected. So when I did that, I click on table and I get the pressure value at all these nodes onto a table format. So what I will do is export all that into on my structural models. I will convert that on the structural load. So let's create a structural model. So I open a new model. I just import again my structural model, and I will go quickly by assigning the boundary condition for the structural analysis. So the constraint condition, so this will be basically fixed at this point. Fixed. Then next thing is to assign the material, so I'll use material by default, property, 3D property. Okay. Now let's mesh this model. Okay. Click on OK. And now I can put my CFD load pressure on it. So to do that, go in the static heat analysis tab, and you have a specific type of static load which is called from result. So click on that, click on interpolation tab. The result tab is normal pressure scalar, 3D element face. Now I select all the 3D elements. Now I have to go again in my table view. Click on Ctrl+C to copy the data here, and click once in this window and click on Ctrl+V to paste the data. So now you get the data from CFD on this, and you click on OK, and you see it has been assigned on my structural model. So this is an interpolation load that I will use to get the result from CFD. So now the only thing I have to do is to create a linear static analysis and solve it. So I give a name, I save it. Now I wait 1 second that the solver give me the result. Sorry, 2 seconds. And you see I get the deformation of the structural model. So this is the total translation. This is the von Mises stress. and the safety factor. So in this specific case, the displacement is quite small, so actually you don't need to worry for a solar panel, but you have to think also that I used steel, and this is a very kind of block, so it's a simplified version, so it's not really realistic model, but anyway, you have the way now to perform such analysis. Okay, now is there some question about that? If you have some question, please ask, and I will answer in direct. Okay, so if there's no question, I'll continue just on the PPT, and I will answer at the end to your questions. Okay, so now I finished this analysis. Okay, I have only okay, I'll answer the question at the end. Before that, I will continue the presentation. And okay, so this demonstration is finished. So I'll go to the last part of this webinar, is the what have been implemented in the NFX 2014, so the new functions. So I know some of you are waiting that, and I prepared this for you. So the first thing is we have a lot of new features, so I only present the main new addition. As I was telling you, NFX CFD is evolving quite fast, and a lot of new features are added every year, so if you don't have what you need, maybe you will have it very soon. So first thing is called MRF, Moving Reference Frame, Porous Media, and fan boundary condition, and the GPU parallel computing. So I'll explain all that. So first of all, what is this moving reference frame? Well, it's a feature that is required when you are doing rotating equipment analysis like fluid machinery, aeronautics, naval industry like propellers, or maybe blowers in industrial machinery. So it's a very useful feature for all that. And to explain to you what it does, I'll give you a simple example. So let's think about this car, which is moving on the road, and you want to know what is the fluid, the velocity fluid around, because you want to know the aerodynamics of the car. So due to that, what you can do is, of course, analyze these aerodynamics like that, but you can think it's very difficult to analyze because you have to put some sensor on your car. The car is moving, the wind is not steady, so you can't really get some result that you can really use. So because of that, what the professionals are doing is that they using a wind tunnel, and then they are just putting the wind on the car. So they are flowing the wind on the car using a big fan, and then analyzing the flow around. So this is exactly the same method that we use for this moving reference frame. Right now in NFX you can simulate rotating equipment using the sliding mesh method, but it's quite it's not simple to modelize, because you have to make a fluid zone which is really rotating, so your mesh is rotating. You have to use the transient analysis type and everything, so it takes time. And in the second type, the MRF, what it does is that your part is actually fixed, so it's not rotating, but the fluid is kind of rotating using this MRF. So it's rotating the fluid instead of rotating the object. So it's the same kind of thing. Now, a small comparison. So if you use the method we have in now, the sliding mesh method, and you compare it to the MRF with the same number of elements, you see the results are almost the same. So you have the same distribution, but you have a big difference in the computation time. The sliding method will take 220 minutes, whereas the MRF method will take 45 minutes. So it's like 5 times faster than before. So it's really a big improvement for those who are doing such analysis. Now the second type of improvement is the porous media that have been added. So porous media are useful if you have catalysts, exhaust system or heat exchanger or perforated plates or filters. So if you want to analyze all that, you need to use the porous media. Why? Well, very simple, because when you have a real model, so let's say you have a real model which you model integrally in CAD, so every small hole is modeled in the CAD, and then you make the finite element model, you see the model is very big. So we did it, and it's around 33 million elements. So basically you can analyze that in NFX, but you'll need a very good computer workstation to do that. So now with the porous media, so it's actually very easy to simulate because you input the law of the porous media directly into the mesh, and you don't need to create a small hole. So you only mesh it as if it was a fluid part, but it's actually a porous media part. So it reduces the number of elements to 4.49 million elements. Now, let's say we did some tests, and this is a kind of plant equipment. So you have a filter here of diameter 14 meter and diameter 6 meter. So the model is 1.7 million elements, and we did the test with this porous media, and you have a small animation here. We show you that the thread is actually stopped by the porous media, and then so velocity is decreased. Now the third improvement is the fan boundary condition. So for equipment heating or cooling, or maybe room ventilation, or if you're doing garage or building ventilation, all that, you need to have a fan model. What it does, it actually, instead of simulating the real fan, it gives you simple fan setting using boundary conditions only. So if you simulate using that, the sliding mesh, so the same method that I taught, you can do it, but you need to have the RPM info, and the calculation time will be quite extended. So what you can do using this new fan inlet is actually replacing this by a mass inlet. So you only need the mass inlet info, how many mass is flowing through this aperture. So, but in the design stage, what you have is that. So how you can simulate the fan using only this. So this is one of the challenge of the designers. Well, using this fan boundary condition, you have this model, you have some simple model of the fan. You can directly input the fan curve into NFX. So the same fan curve that is given in this documentation, and then you can simulate it. So this is what it gives, and you can go your results. So the flow rate is automatically determined. So this is an application that we did to test that. So it's a PCB cooling. So you see there's a lot of parts inside, so solid parts, and of course coupled with heat transfer to see the effect of the fan. And the last improvement, but not the least, is what is called the GPU calculation. So you have conventional HPC, so high processing computing. So this kind of server is very big and very costly because you have some hardware, some software to buy. You have a lot of maintenance costs, and it will depreciate and difficult to amortize. But what you have a more simple solution, which is called a GPU computing, and GPU means graphical processor unit. So it's using the graphical processor of your graphic card to compute the result. So basically, such GPU, so the one we recommend is the NVIDIA Tesla, which is the best to work with NFX. So NFX is only compatible with NVIDIA, and Tesla is the one which is, let's say, optimized for scientific calculations. So this is the one you need if you want to get the GPU computing on CFD or in structural. So what is important is the double precision. So here of your graphic card. So here 0.5 teraflops, and here you have the CPU. So it has much more cores than the CPU, but it uses a different way to calculate. So this is why it requires specific algorithm to solve the problem using the GPU. So you have a high performance increase, and you can compare it to a low cost of investment and low maintenance cost. So of course we did some speed benchmark. So this is a GPU test. The mesh elements were 2 million, so 2 million elements, and this is a heat cooling analysis. The CPU we use is the Xeon 2.93 GHz and a Tesla GPU of 0.5 teraflops. So I precise that this is not the best Tesla right now. There's a better one of 1.5, which is giving you 2 or 3 times even more better result than that. So this is the computation time when you use only the CPU, the 1 core, 2 core, 3 core, and 4 cores. But if you use CPU plus GPU, you have an improvement of around 5 times faster if you have 4 cores in your computer. So it's really for a big CFD model which could take hours to solve. If you multiply by 5, the time to solve it's really not neglectable, so it's really good. Okay, so it's almost over for this webinar, and now I'll present in one slide where you can get more training material, because some of you are asking this question. So this is midasnfx.com, our website. So first of all, you go in the tutorial section and you'll get more tutorials about CFD. So right now we have 7 tutorials, so if you want to get more in-depth in the CFD analysis, you can go here. We have also e-learning, so the webinar you're watching right now. We have more webinar planned for next month, so the next one will be about composites. So you can go on the website in the Try e-learning section to register for the next sessions if you're interested and to see what we're planning. So we'll have a lot of good webinars, others about CFD and also thermal coupled webinar and everything. And if you're not an NFX user right now, you can download the NFX trial for 30 days, which is available on Midas NFX website as well. So if you apply, you will receive directly the trial. You can install it on your computer and directly start the trial period. Okay, thank you very much for this webinar. Now it's a question and answer section. So I'm waiting for your question. You can write it in the question section and I'll be answering them right now. So don't be afraid. If you have some questions, just write them and we'll be here to answer them. By the way, you see that the next week webinar have been featured on NAFEMS. So if you go on NAFEMS website, on the first page, you'll see our invitation to this composite webinar. And if you want, you can join us on the social networks as well. Okay, so there's some questions. Do we have a way to know the flow regime after the deformation. Yes, you have some way to do that in NFX, and we will send you the information by email on how to do that. Do you have an integrated fan library? We don't have library, but we have the possibility to import the curve. So if you have the curve, fan curve, you can import directly in it. And okay, there's someone asking for which Tesla model I used, K20 or K40. So right now we are using the K20, but the best one is the K40. So K40 will give you around 3 times more improvement than what we have in this, than the benchmark we have. Well, unfortunately, we requested to have this new Tesla, but we didn't got it. So maybe next time we will send the benchmark about it. Can we simulate the internal flow inside a model imported from another CAD software? Yes, of course you can do it. So you can just import your CAD model and use create a CFD section, and then you will be able to create a fluid volume inside your model. So we have a tutorial about that on the website, so you can download it to check how to do. Is there more questions? Don't be afraid to ask if you have something in the head and you'd like to know the answer. So if you ask the answer to life, I will answer you 42, but you can ask any question about CFD. Okay, no more questions. So thank you very much for attending. I hope you enjoyed this session, and I hope to see you in the next webinar session that we planned. We have a lot of good webinars about composite, about explicit analysis, nonlinear dynamic, thermal analysis, everything. So it will be really interesting, and I hope you will join them. Goodbye and see you next time.